All right, everybody. So we started talking about differential equations last time. And so one question is why? One of our basic strategies for dealing with a PDE is that we will break it down into multiple differential equations. So this first order case is kind of a fundamental case, because by using this ODE technique of separation of variables here, so here with the original PDE, I put all the y variables on one side and everybody else on the other. So this y variable goes downstairs. And now when we integrate, this integrates to the natural log. And on the other side, we integrate x plus c. So then after we exponentiate everything, so now exponentiate everything, and we end up with our solution involving the exponential function. So here we exponentiate and then just break out the term with the constant. And eventually we can simplify it down to this. And here, the whole reason I did this is because this form of solution is very important. That for the first order, we're able to solve it using a function of the form e raised to a constant times x. That's going to be a canonical solution form. And one thing to remember in ODEs or PDEs, and I don't know, I think in math in general, is once we find a solution is to verify that it does indeed satisfy the original differential equation. Sometimes there are solution techniques that can lead to a function, but the function may not converge or actually satisfy the original underlying problem. So here's some theory stuff. So the stuff that's going to show up here in the next couple of slides is extremely important. We will use this theory throughout the course. So for the general solution, there was a constant that showed up. And so that's known as the free constant. And so the number of free constants usually correspond to the order of the differential equation. So for a second order differential equation, for example, you have y double prime plus y prime. Here we would expect to see two free constants. So here I want to define what it means to be a solution of a linear ODE. There are many ways to define the notion of a solution. This is one way, and this is what we would call a classical solution. But this is not the only way to define a solution for differential equations. So this would be a classical solution. So here, for a order n ODE, so the highest derivative is to the nth power, is the nth derivative. We are looking for a function that is differentiable, that can be differentiated n times, that the function and its derivatives satisfy the given problem, in the domain specified. And we expect to see exactly n free constants here. And so the free constants are a result of not having enough information. This is like in calculus when you integrate and you get a plus c. We don't know what that constant is unless we're given more information. So here, more information typically comes in the form of what we call an initial condition and or boundary conditions. So an initial condition is, here ideally in a differential equation, we assume the independent variable is time. It's not necessarily, and it won't be in the PDEs that we do. But here the idea is we call it an initial condition because we're wondering what's happening with the solution at time t equal to 0. So once we're given an initial condition, or, in this case, we had one free constant. So with one initial condition, we're able to solve and go from a general solution to a specific solution. So here we initially had a general solution, then with the initial condition, we're able to narrow it down to one specific function. Again, we still need to verify. And there are other questions. Do we know this is a unique solution? Do we know this is the only solution? And depending on the information we're given, if we're given contradictory information, then it's possible that the differential equation not have any solution. So here I've given sort of contradictory information where there's no one constant that'll satisfy y1 equal to 3 and y2 equal to 0. The exponential function is never going to equal 0. So in this case, there's no solution. But this is a toy problem that I was purposely trying to give you a problem where it breaks. The other type of information that we can be given is called boundary conditions. And so that's typically the behavior of the function on the boundary of our domain. Also, so for example, here, if we assume the solution should be bounded, then the exponential function, the only way it'll be a solution is if alpha is equal to 0. So if we want this exponential function to be bounded, we know the exponential is not bounded, function is not bounded. So the only way to force it is to have alpha be equal to 0, and then we get the trivial solution. So in this kind of boring first order case, requiring a bounded solution is not fun. But or a second order case. So now let me talk now about the this is now really important now. The solution structure, the underlying way we organize the solutions of these differential equations. So the stuff we do on this slide and the next slide are super, super important. Okay, we're going to use this every time throughout the rest of the semester. Okay, so this superposition is extremely important. Okay, so just to remind you, a vector space is a set equipped with two operations. Namely, we have vector addition, that is for any two vectors, say v and w, we can add them. That is to say, an addition is defined. And second, that the addition is closed. That is to say, after adding the two vectors, we get back an element of the original set v. So here's a kind of example that doesn't quite work, but if you add even numbers, you always get an even number. But if you add two odd numbers, you get an even number. So odd numbers under pairwise addition aren't closed. The other operation would be scalar to vector multiplication. So for any real number c, we define this notion of multiplying the vector by a scalar. So that's saying two things. One, that we've have a well-defined way of doing that. Given a vector, I have a well-defined way of multiplying it by a scalar. And here, when I say vector, it could be, a function or a matrix, right? A vector is a generic term, right? And the second thing is that this operation is closed, that when I multiply the vector by a scalar, we end up back in the original set V. So, a vector space is also equipped with some axioms, such as commutativity of addition, the existence of a zero vector, and I'll let you review that stuff. But it's all the properties we're used to from the real numbers, because the real numbers are a vector space. So here's a very important example of a vector space. It's a function space. So what does that mean? It means the vectors here are actually functions. Okay, so here, we use the notation, so this notation is important, c raised to the n of r. That indicates that we have a function whose domain is the reals, and it has n continuous derivatives. So the n tells you how many derivatives, the big capital C is for continuous. And then the r here, that's the domain of the function. So these are functions over the reals that you can differentiate n times, and each of those derivatives is continuous. So we can organize this as a vector space under the usual rules of function addition and scalar multiplication of functions. And why are we interested in this space? Because this is essentially the space where our solutions are going to live. We're looking for differentiable functions that satisfy a differential equation or a PDE. Well, then we're going to have to look at the space of continuous functions. So that's why this is even relevant, that this is where we're going to look for solutions. So now let me define the notion of a linear operator or linear function. So suppose we have two vector spaces now. So remember this vector space stuff for matrix methods? I told you you're going to use all the math you did. We have two vector spaces, V and W. So I called it a function here. Typically, we would call it an operator or a map, but we can call it a function or operator, L going from V to W. So what does this notation mean? I can't remember if we talked about this notation. So this means L is the name of the function, V is the domain, and W is the target space. So L of V will be in W. And so we call this function linear if for any vectors U and little v in capital V. So, make sure you keep your apples and oranges straight. Make sure you know which vector space you're in, little v or, capital V or capital W. So here, linearity, L is linear if L of U plus V equals L of U plus L of V. So here, think about it now. L of U is in capital W. This is in W, right? So this is saying L respects addition. If you do addition in V, that translates to addition in W under the function L. And here, L of C times U is C times L of U. Again, think about where these vectors are. Here, C times L of U, C times L of U is in W, whereas this vector in here, that's in V.
Dr. Bott?
Yes, sir.
Is this analogous to a ring in algebra? Are there any additional constraints?
Yes. So this is, let me see, I believe this is a ring. This is a ring. This is some type of ring in abstract algebra. It's a ring over a module, I believe is the correct term. A vector space is a ring over a module, if I remember my abstract algebra correctly.
Thank you.
Yeah. So so that's a fancy term for vector space. So that you have to put your suit on for that. So indeed, it's a ring over a module. So here now, why do we care about these linear things? Is, well, we're going to look at a lot of linear differential equations. And so, for example, if you look at a differential equation like this, I have y prime plus ay. We can essentially think of that as a function, a function on functions, where the input is some differentiable function, at least C1 in this case, a function y, and the output here is also a function. Since we've taken a derivative, at best we know it's continuous, C0. So there's your input output, and now we can use linear algebra to quantify solutions to equations involving this function or linear operator. So we start by solving what's called the homogeneous equation. So this, should kind of seem familiar because we did this procedure in regular differential equations so many times, where we would find a homogeneous equation, find a particular solution, and then add the two. And the whole reason that works is because of the linearity. So here, the homogeneous equation is when we take the differential equation or PDE and set it equal to 0. So that's known as the homogeneous equation. This is like trying to find the kernel of a matrix. You say AX equal to 0. Here we're finding the kernel of the linear operator L. And here, we can't have matrices here because these function spaces are infinite dimensional. Essentially, you can think of Fourier series as linear algebra of infinite dimensional vector spaces. In matrix methods or linear algebra, we typically restricted ourselves to finite dimensional vector spaces. And so that's the big difference here in Fourier series. We're now working over infinite dimensional vector spaces. So we can't use matrices to represent these things. So here, for y prime plus alpha y, if you look at the homogeneous equation, we get back the ODE that we solved a few slides ago. So every linear, you can take an ODE and break it down into a kind of a homogeneous component and a component that's not homogeneous, and solve each separately. So here, this is to kind of show you the connection between the ODE that we solved and linear operators, which is kind of what's happening in the background this whole time. Okay, so here's the big thing, the superposition principle, which I'll mention a million times. So suppose we have, in this case, we have finitely many n individual solutions to the homogeneous equation. Then any linear combination. So linear combinations, when you take the scalar, multiply it to a vector, and then potentially add it to another scalar times vector. So here, any linear combination will then again be a solution. And this is completely a result of the linearity. You say, why is this true? It's because of the linearity. Okay, so this will be one of the underpinnings of how we build a Fourier series. So when we use the superposition principle, so this is important now, we won't have n individual solutions, we'll have infinitely many individual solutions. And they'll all be of the form cosine of some number times x, cosine nx, or sine nx. And there'll be infinitely many of them. And so the superposition principle says any linear combination of these solutions will again be a solution. So then we'll take a linear combination of these infinitely many cosines and sines and create this gigantic sum of cosine functions and sine functions. And that infinite series is a Fourier series. Okay, so this superposition principle is the theoretical underpinning from linear algebra that allows us to build the superposition solution that we call a Fourier series. Let me solve a second order differential equation. So we'll solve a lot of second order stuff. Okay, so this is really a very relevant problem. And so this is also the reason I solved the first order problem. So let me show you. Here, we want to solve this homogeneous equation, y double prime minus lambda y equal to 0. We're solving that homogeneous equation. And so the first step is to assume the solution has the form y equal to e to the rx. And it's a perfectly natural question now to ask and say, hey, where'd you get y e to the rx? Where'd that come from? And so this is motivated, this form is motivated by the solution to the first order equation, which we did using regular separation of variables for ODEs. There we got c e to the minus alpha x. So we're using this idea that it's e to a constant times x. That's kind of a, some kind of starting point for us. Because it worked once, maybe it'll work again. So assuming y equal to e to the rx, where r is to be determined, if we plug it into the ODE, we get this equation. So the derivative of e to the rx is r e to the rx. So if we do two derivatives, I get r times r e to the rx, or r squared e to the rx. On the other side, we just have lambda times e to the rx. And so now we can cancel the e to the rx on both sides. And we get lambda squared equal, r squared equal to lambda. And then so we take the square root, you get r is equal to plus minus lambda. So I will say, at this point, we should be really careful. At this point, depending on whether lambda is positive, 0, or negative, different things will happen. But we're not getting into those details right now. Okay, so here I just want to give you an overview of this procedure that we'll do many, 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 many times. Okay, so now we've essentially found two solutions. We assume the solution had the form e to the rx. By plugging it into the PDE, the ODE, we were able to solve for r. And so now I have my two solutions. And this is a second order ODE, so I do expect two solutions. And so now by the superposition principle, a linear combination of these two solutions will be a general solution. And this procedure that we just did is a miniature version of the procedure we'll do over and over again to solve PDEs to find a Fourier series. At the end, when we take our linear combinations, we'll end up with linear combinations of cosines and sines. So we do this with PDEs. So, by the way, just for future use, we could also, because any linear combination of these work, we could also write it in the form cosh lambda x and sinh lambda x. Remember that cosh lambda x, this is e to the square root lambda x plus e to the minus square root lambda x over 2. So my point here is that it's a linear combination of solutions. So by superposition principle, this is just another way of writing, so in terms of linear algebra language, e to the square root lambda x and e to the minus square root lambda x are a basis for the solutions, but bases aren't unique. So here we have a two-dimensional solution space. So any two functions in this space that are linearly independent will also form a basis. So here we can form cosh and sinh by averaging e to the squared lambda x and e to the minus squared lambda x over 2. That's for cosh. And for sinh, that's e to the squared lambda x minus e to the minus squared lambda x over 2. So those are in the function space. Those can be shown to be linearly independent. So those functions are also a basis for the solution space. So yes. So the question now is, are there certain situations where we want to write the solution in one form and not the other? And there are. So when we actually solve the PDE, I will show you where in certain situations it's more beneficial to, because of the certain geometry involved, it's more beneficial to write it in terms of cosh or sinh. So it isn't strictly a matter of preference. It could be, but there are also technical benefits to it. So yeah. So, and this cosh sinh stuff we won't use right away. It'll come up when we solve the Laplace's equation, which happens a little bit later in the semester. But just to remind you, we could also, using the superposition principle, pose the solution as a hyperbolic functions. So almost done. Here's only two more slides left here, and then I want to switch to Fourier series. So let me talk about the notion of solutions and when we have unique solutions. So essentially the idea is we need as many initial conditions as we have free constants. So I have two free constants, then I have two unknown variables. I would need two pieces of information to find those two. I don't want to call them variables, I should call them parameters, probably a better term. So in the previous ODE, we solved y of x equals c1 e to the squared lambda x plus c2 e to the minus squared lambda x. So c1 and c2 are two free constants. So now if we're given two pieces of information, it could be initial, two pieces of information about the variable y or about y prime. The information can be given in different forms, So here we're given information about y and its derivative. So these are all initial conditions, initial condition of the original function and initial condition of the derivative. And then through simple algebra, we can find the maybe a little bit of calculus, we can find the coefficients and find the solution. So linear independence, I've already mentioned it. Maybe I should have given this definition first, just to remind you the definition of linear independence. The idea behind linearly independent is that if you think about two functions, that essentially they're not really overlapping, that they're not covering the same ground. So here, the technical definition here is any linear combination, if we take c1 times y1 of x, all the way up to cn yn of x, this will be equal to 0 for all x. That part's really important. We want to know for all x, can I find some linear combinations of these functions so that they'll cancel each other out? If there aren't any combinations, if the only way to make this sum equal to 0 is by forcing all the constants to be 0, then the functions are linearly independent. And here what we're saying is there's no way to use some of the functions to cancel out other functions. The only way to zero out a sum of these functions is to force each of the function to be strictly equal to 0. And that's this notion of linear independence. There's no shared information between the functions. There might be overlap, but only a little bit. So for a linear homogeneous differential equation of order n, here the theory tells us it will have exactly n linearly independent solutions. we can prove that the dimension of the solution space is capital N. And because of that, we know it'll have to have n linearly independent solutions. These linear independent solutions will form a basis. When we're solving PDEs, we won't have n solutions, we'll have infinitely many solutions. And we'll, take a linear combination of those will give us our Fourier series. And here, if we have an order n differential equation, then we need n pieces of information, n initial conditions, to find the n unknown free constants that'll come as baggage with this nth order differential equation. So in a perfect world, we're looking for initial conditions like this across the orders of the function. In a perfect world, some information about the function, its derivative, its second derivative, all the way up to the n minus first derivative at a fixed point x of 0. Sorry, one second. My apologies. So here, it is possible to get a situation. So in matrix methods, you remember the fundamental lesson in matrix methods is that when we solve linear systems, there's only three possibilities. You have one solution, you have infinitely many solutions, or you have no solutions. So here, by playing games with the boundary conditions, you can also create those situations. If we give boundary conditions at more than one location. So here we have boundary condition at x sub 0. That's one location. Suppose we also have information at another point x sub 1. So that's what I mean by two or more locations, two or more spatial locations. Then, depending on the situation, you could have no solution or one solution or infinitely many solutions. It just depends on how all the boundary conditions fit with the solution. This is math, so we can always break the system. We can always pose a problem that doesn't make sense. And we wanna at least intellectually observe those pathological cases for the sake of learning about them. And so that's why I'm talking about this here. We won't actually have a situation like this, but it's possible. You could see like where they'll just do that as a trick question or something just to mess with someone. Not me, but someone that's not nice. So let's talk about the complex plane real quick. Why? Because at the end of the semester, we're going to look at the complex version of the Fourier series. Okay, so let's do this really quick. The complex plane is based on the definition of the imaginary number. So I is defined to be a number such that I squared equal to -1. Right? So I is known as an imaginary number or a Gaussian integer. And we can form a complex number by having a number that has a purely real part. So here I have a plus ib. So a is the real part and ib is the complex part. So b is a real number, but when we multiply it by I, it becomes a complex number. So the module, so there's the picture. Really the complex plane and R2 are essentially very similar. The vertical axis here is our complex axis. The horizontal axis are our real numbers. And so you find, here's my real part, my imaginary part. The intersection of those two is the point on the complex plane. So the difference between the complex numbers and the reals, how we talk about the real line? There's no complex line. When you talk about complex, it only lives on a plane. It doesn't get smaller than a plane. Its minimum dimension is 2. Whereas the real line, can be a line, its dimension is 1. So here we can define the idea of a absolute value. It's just called the modulus. And so given a complex number, if you change the sign in between the real and imaginary part, that's called a conjugate. And if you multiply a complex number to its conjugate and take the positive square root, you get, so when you multiply a number to its conjugate, you get a real number. And then when you take that's non-negative, and you take the square root, it's like finding the distance from the origin. It's essentially like an absolute value. I haven't ever heard of the imaginary line. So the question is there an imaginary line? Because we talk about the real line. The imaginary line, I assume mathematically would be interpreted as a subset of the complex plane. Yeah, I haven't, that's a great question. Is there an imaginary line? So I don't know. That's a good one. Thanks for that. So the modulus just, like I said, gives us basically this distance from the center is that modulus, is norm z. We also call it rho. Rho r for radius, right? And theta here we can use, so we can write z as alpha plus I beta, but we can also use sort of these type of polar coordinates I'll show you using the angle and the distance from the center. So we're at the very last slide here. And so if you think this is totally random, it seems like it, but I promise we'll use all of this stuff during the semester. Okay, so very last slide here. Using a Maclaurin series, we can prove Euler's formula, which says e to the I theta is equal to cosine theta plus I sine theta, right? Math majors, please don't get this tattooed on your body. And here, the magnitude, if you calculate the modulus, okay, if you do the math, you get the modulus is cosine squared plus sine squared. So here what I'm doing is I'm multiplying cosine theta times cosine minus I sine theta. So then I get cosine squared minus I squared sine squared, but I squared is -1. So I get cosine squared minus sine squared. I get cosine squared plus sine squared. The modulus is 1. So this term always just lives on a circle, okay? It's always exactly 1 unit away from the origin, e to the I theta. For any theta, e to the I theta always lives on circle of radius 1. And so we can rewrite z a plus ib. Here, if we use a little trigonometry. So here, if you look at theta, remember cosine of theta, cosine is adjacent over hypotenuse. So cosine of theta would be a over rho. Now take the rho and move it over. This is just like with polar coordinates, right? You get r cosine theta. Here we have a equals rho cosine theta. And so I'm going to replace this a right here with rho cosine theta. Similarly, sine theta would be opposite over hypotenuse for sine theta. So you have opposite over the hypotenuse. That gives you b over rho. Move the rho over, I get b equals rho sine theta. Replace this b here with rho sine theta. Finally, factor out the rho, and we can also write the point in, this is sort of like polar coordinates, as rho times e to the I theta, where rho is like r in your polar coordinates. It's the distance from the pole. The origin in polar coordinates is called the pole, and theta is the angle with the polar axis. So yeah, we'll use this later. Don't worry about it. If you don't like it, don't worry about it. We'll use it way at the end just for a little bit of Fourier series in complex numbers. All right, so that ends the review. And I know it was a little bit long, but all that stuff we will use. So I think it was important to review all that stuff. And, you know, certainly when the time comes, when you need that material, certainly it's good to go back to it, you know, take a look at it. So I'm going to switch over now and finally talk about some Fourier series. And this will probably be one of the greatest moments of your life. So make a note in your journal, everybody. So here we go. Fourier series and orthogonal vectors. Yay! So underneath I say notes on Fourier series. What the heck does that mean? So Harvey Seeger, who, you know, essentially originated this course, he kind of started teaching this course 25 years ago or something. He wrote a set of notes on Fourier series. So these are Seeger's notes on Fourier series. There's 7 quote unquote chapters. So these 7 chapters cover the analysis, the real dry analysis that makes up the initial part of this course. And then around the 4th week of this course, we'll finally start solving PDEs, okay? So these are my notes on Harvey Seeger's notes on Fourier series. That's right, these are notes on Fourier series. And if you're taking notes, guess what? Notes on Fourier series, congratulations. Okay, here we go. So first and foremost, let's talk about infinite dimensional vector spaces, because Really, that's what this class is about. This class is going to be called infinite dimensional vector spaces, okay? So for two continuous functions, I want to define what's called the L2 inner product. L stands for the word Lebesgue, which is the last name of a French mathematician, okay? L2 inner product on this interval AB, we define it to be basically just the integral of the product of the functions, okay? So here's the notation for inner product, and now it's just defined to be this integral of f times g, okay? And the norm, which is like an absolute value, is defined to be just the positive square root of f inner product with itself. And we have this, norm notation reserved there. Here, the 2 indicates this square is kind of part of what's going on with this. The square and the square root is what the 2 indicates. Okay, so let's define a Fourier basis. So first of all, I want you to notice we're going to use the variable z for now. It's not a complex number. Z is a real number. And we're restricting ourselves to minus pi to pi. I want you to set aside all your concerns, okay? Because you're like, wait, why minus pi to pi, blah, blah. I want you to just set all that aside and we'll get to it, okay? It's a long story. So the Fourier basis is defined as this infinite set of functions involving the cosine and sine. I have the number 1, which we can think of as cosine 0. Sine 0 is just 0. And you can think of the number 1 as cosine 0z. Then I have cosine z and sine z. So to think about, there's a 1 in front. Cosine 2z, sine 2z, and so on and so forth. Cosine 3z, sine 3z. In general, it's the set cosine nz, sine nz, n going from 1 to infinity with the number 1 thrown in there. Or I guess you want to say n equal to 0, that's fine. 0 isn't in the set, 1 is in the set. So this infinite set of functions forms what we call the Fourier basis. These numbers here, the 1, the 2, those are called wave numbers. So, cosine and sine, think about the graph, these are waves, so we call these wave numbers. So those wave numbers determine the periodicity, or frequency of the waves and the wavelength. I guess periodicity and wavelength are the same. So just to get all technical and formal on you, this set of function forms what we call an infinite, countably infinite, I should say, mutually orthogonal basis of the vector space of continuous functions, over the domain minus pi to pi. What does that mean? Well, it means, the basis part means that I can take any continuous function that's defined on minus pi to pi and write it as a linear combination of these bases of 1 cosine sine, cosine 2 z sine 2, and write it as a linear combination. That's what the basis part means. The mutually orthogonal part means that when you take the inner product of any 2 basis vectors, if they are different, then the inner product is 0. If the 2 basis vectors are the same, then the inner product is not 0. So here, and Haberman has done these calculations for you in the book. You'll do these calculations on the homework. So here we can show that the inner product of sine nz and sine mz, if n and m are different, this will equal 0. How do you do this integral? You can use one of those trig identities we talked about in the review, or you can actually, because you're dealing with periodic functions, use an integration by parts trick where you do integration by parts twice, which is what I've asked you to do in the homework. And so when n is not equal to m, you can show they're 0, or when n is equal to m, we can show they're not 0. They happen to be equal to pi, that's great. We really don't care too much. That'll just be what we call a normalizing constant, just that it's not 0 when they are equal. Similarly for cosine, we look at the inner product between the 2. It's 0 when n is not equal to m, and it's non-zero when n is equal to n. And finally, we compare the sines and cosines. Those are 0, and they're different basis functions. The sine is a different basis function from cosine. So for orthogonality, we expect the inner product to be 0. That's what we have here because the integral is easy. Remember, sine's an odd function, cosine's an even function. The product is an odd function. The integral of an odd function from minus a to a is always 0 because the area above and below cancel. And then finally, the last basis function is 1. We can show the inner product of 1 with cosine is 0, and the inner product of 1 with sine is 0. Cosine, the integral is 0 between minus pi and pi, because again, you had this nice symmetry where things cancel out. And for sine as well. So those are all Calc 1 integrals that you can do in multiple ways, and you'll work on those in the homework. Let me show you an actual example now as to how orthogonality helps us at all. It's really important that you get out of this class appreciating orthogonality, and that orthogonality, is that we really take advantage of it. Okay, here we go. So I'm posing a toy problem here. So I'm going to go ahead and assume that we have some continuous function f of z. Z is a real number. And I'm going to assume that it's equal to this Fourier series. So this thing right here is called a Fourier series. This gigantic infinite sum. And you can see it's a linear combination of the Fourier basis. So I shouldn't write the basis this way. I wrote it this way. This is really not correct because, and I'll fix this typo. I should be careful because this implies 0 is in the set because sine of 0 is 0, and no set of basis vectors can contain the 0 vector. Okay, so this notation is, bad G. I should make this a 1 and then union this with 1. It's a mess. I'll rewrite it so it's nicer. Okay, so my bad. So think about it. No set of basis vectors can contain the 0 vector. Okay, it violates the linear independence part of it. Anywho, so this is called a Fourier series. It's a linear combination of all the basis elements. A sub 0, think of this as a sub 0 times 1. And then here a sub n is multiplying all the cosine basis elements. B sub n is multiplying all the sine basis elements. Here we start at 1, and then here's your basis element 1. Okay, so assume f of z equals this Fourier series for z between minus pi and pi. I'm doing this toy problem. What I want to do is find a formula for a sub 8. Why a sub 8? 8's my favorite number. Why is it my favorite number? 2 cubed. What's cooler than 2 cubed, y'all? It's got 2 and 3. Okay, so, and of course this formula will work for any coefficient, right? So here's the orthogonality at work. It's just really cool here. For a sub 8, the corresponding basis function that's associated to a sub 8 is cosine 8z, right? Here, if you make n equal to 8, then here I'm going to have cosine 8z, right? So let's multiply both sides of the equation by cosine 8z. Why? I'll show you. So multiply both sides of the equation. All right, so here, just here I've got my cosine 8z slapped on both sides. Okay. Now integrate both sides of the equation from negative pi to pi. So now we have this mess. Okay. And assume we can interchange here. We can bring the integral inside the sum. Just assume we can do that for now. And now I want to show you the orthogonality kicks in big time. So now if we look at these integrals, all of the integrals that are sine times cosine, those are all 0 because of the orthogonality. These completely disappear and 0 out. And for all the other terms, the ones that are cosine, again, because of the orthogonality, all of those integrals will be 0, including this first integral, will be 0 except when n is equal to 8. Right here, when n is the same as 8, then the integral will not equal 0. That's the only time. So this is what our sum ends up looking like. So this sum up here after the orthogonality just becomes a very simple expression. And this is purely because of the orthogonality. And now remember what I'm trying to do here. I now want to isolate this constant a sub 8. So I'm going to pull the constant out of the integral and then isolate the constant by dividing both sides, dividing the integral away. So here I have my formula for a sub 8. It's the integral on the left-hand side divided by the integral, that a sub 8 was the coefficient of. And we can write this in terms of our inner product notation in the following way. The numerator is f of z inner product cosine 8z divided by the norm of cosine 8z squared. This is a projection formula. This is basically the same projection formula you had in Calc 3. Except in Calc 3, the inner product was a dot product, and you were over the finite dimensional vector space R sub n. So yeah, that's a Fourier series. That's why, and I proved the same result generically, just in general, but, and I'm done here. So I'm just gonna jump ahead here. So this is your formal definition of the Fourier series. It's a series like a Maclaurin series, except it's not a power series. This series is known as a trigonometric polynomial. It's not a polynomial in the traditional sense, but it's called a trigonometric polynomial, where the n, the wave number, is like the degree. And so these are the formulas. What's nice about Fourier series, for Taylor series, you have to take the derivatives, and there's this kind of annoying formula. Here we can find the coefficients by integrating. Okay. So there is one Fourier series problem on the homework, and you would use these formulas to find it. And, integration by parts is required. So yeah, I'm over time, so I'm over time, right? Do I stop at 11:10? What time?
You have like 2 minutes.
I have 2 minutes. Okay, so I'm basically done. So I'm not gonna rush it, but so yeah, take a look at this example. Is really helpful to understand why orthogonality helps. And then take a look at this slide for just what are the formulas for how you find a Fourier series. And this slide in the middle, this is where I'll pick it up next time. Here I proved the exact same projection formula, but I just did it very generically, where I'm not, because you can do this Fourier series idea with essentially any orthogonal basis. Okay, folks, I'm going to stop talking. All right, I'll stop right here. Thank you for your time, everybody. I'm going to stop right here.